Let me first introduce Trevor Lanting. There's Trevor and Ashley and Elijah. Great. So Trevor is the Chief Development Officer in DWave. He leads DWave's product development organization, which includes teams responsible for software systems and cloud services. Trevor joined DWave in 2008 and previously served as SVP of Software Algorithms and Cloud Services and Vice President of Science. Trevor has helped drive the development and deployment of 5 generations of annealing quantum computing systems and specializes in connecting fundamental research results and insights with real-world applications. He holds a Bachelor's of Science in Physics and Astronomy from the University of British Columbia and a PhD in Physics from the University of California at Berkeley. And he will be our first speaker. But before that, let me introduce Ashley Nicole Warner, who is there with Trevor. She joined DWave in 2024 as an experimental physicist, coming from a background in materials science and failure analysis before entering the field of quantum computing. She earned her bachelor's in physics from UC San Diego and has a master's in condensed matter physics from the University of British Columbia. At DWave, she investigates the microscopic structure of various materials to understand and eliminate sources of noise with the goal of enhancing coherence times in quantum processors. Finally, a special welcome to Elijah Pawlowski. Elijah is a research scientist at Los Alamos National Laboratory in the Information Systems and Modeling Division. His research interests include quantum computing, quantum algorithms, cybersecurity, and machine learning. And he will be our third speaker this morning. So with that, we'll get started with Trevor. And again, if you have questions, please put them in the Q&A box.
Great. Thank you, Susan. And thanks to everyone for joining this morning. The three of us and everyone at DWave is very excited to talk to you about our latest annealing quantum computing product, our 6th generation product, Advantage2. I'm going to start for the first few minutes doing a deeper dive on the Advantage2 technology. And then, like Susan said, turn it over to Ashley. 2 and a bit weeks ago, we released our Advantage2 annealing quantum computing system. This is our 6th generation quantum computing system, and it represents a giant step in performance. And this has got us incredibly excited. This system is able to solve problems well beyond the reach of classical methods, and we're seeing significant performance gains in the Advantage2 technology over previous generations of annealing quantum computing system. Specifically, the 2 key areas we pushed on for this technology release are qubit connectivity and qubit coherence. Connectivity is a term that denotes how many qubits each qubit in your fabric is connected to. We want to drive connectivity up because that allows us to represent more complicated problems, represent sort of more complex optimization problems, and do more complex quantum simulation problems. As we drive up connectivity, we see a massive increase in performance across all of the use cases of our technology. The second thrust that we really pushed for Advantage2 was increasing qubit coherence. We've done a lot of work internally, and a lot of researchers externally, and customers externally, have really linked quantum coherence and increasing coherence to increasing performance. And we've been able to more than double the coherence time with Advantage2 over our previous generations of technology by re-engineering our fabrication stack from the ground up. Production-ready Advantage2 processors are now available at the scale of more than 4,400 qubits and are available now to all of our customers via our Leap Cloud platform. So just drilling down into some of the changes and improvements, I spoke a little bit about this already, that we're seeing in Advantage2 that really are key enhancements that set this technology up to perform and improve performance and outperform previous generations of technology. The first is connectivity. So going from 15-way connectivity on our Advantage technology to 20-way connectivity on Advantage2 is really allowing us to solve more complex problems. Both in quantum optimization, we can represent problems with much more dense connection between variables. We can also embed more complex in the fabric of our processors and study their behavior. And so as we drive up connectivity, we're really able to solve increasingly complex problems. Advantage2 has a higher energy scale. This means that there are stronger interactions that we can represent between the qubits. And so this represents or delivers much higher quality solutions over Advantage. We're seeing across all of the Advantage2 chips that we're calibrating and benchmarking a 40% increase in energy scale. The lower noise, higher quality fabrication stack is delivering reduced noise in the fabric of a processor with their qubits. So this results in much higher precision representation of the problems that we can solve with Advantage2. And then more than doubling in coherence really drives a faster time to solution. So across the board, pushing on energy scale, connectivity, and coherence is really paying off in the ability of the Advantage2 technology to solve problems beyond the reach of classical methods and outperform Advantage. So I want to say a couple of words on connectivity. So shown on the left is a representation of the lattice or the qubit structure in the current Advantage2 production solver available in LEAP. More than 4,400 qubits are available in the fabric of this processor and more than 40,000 couplers. Shown on the right is a schematic that denotes the dense connection, that the Zephyr topology, the 20-way connectivity that we built on Advantage2, how this actually looks. What you can see, every one of the orange dots represents a qubit, and every one of the solid black lines represents a connection between qubits. This connection is programmable, it's under user control, and by programming these interactions between the qubits, you can represent incredibly complex interactions between existing qubits. And this dense connection and this increase in a connectivity is a key piece of the improvement that we're delivering with Advantage2. And over the course of the 6 generations of annealing system, we've been progressively increasing the connectivity of the fabric of the processor. And this is directly tied to increasing performance. So this is some benchmarking data that our internal benchmarking team has taken on our Advantage2 processor. In this case, we're taking a canonically hard optimization problem set. In this case, a 3D spin glass, a lattice structure that we're able to embed in Advantage2. We can embed lattices up to 12 by 12 by 12, and we can pose what we call spin glass problems. So these are problems that have very rugged, complex landscapes that are hard to solve via classical methods. And we can actually horse race our Advantage2 technology against Advantage in delivering solutions to these hard problems. So what we're showing on the right here is the results of this horse race, comparing Advantage to Advantage2. Along the y-axis is a measure of relative error. The idea is you want to drive relative error down. As you drive down toward the x-axis, you're getting closer to optimal solutions. And then what we're plotting along the x-axis is annealing time. So this is a proxy for how much time you're spending doing the computation. So I want to make a couple of notes here. Well, the first is that the blue data are coming from our previous generation Advantage production systems. The orange data are coming from Advantage2. Across all annealing times, we're seeing a substantial improvement, a reduction in relative error with the Advantage2 processor over Advantage. But the other thing to note is that if you basically pick a particular threshold of relative error, so in this case, we're picking something just below 10%, and then you basically measure the amount of time you need to spend getting to that relative error for Advantage versus Advantage2. We're seeing orders of magnitude for this problem set up to 10,000 times faster times to solution to get to this relative error over Advantage. And this really is driven by the increased energy scale and the increased coherence of the processor. So these are driving not just sort of marginal or small increases in performance, but performance that is orders of magnitude better over previous technology. I'll speak a little bit about the fast anneal protocol, but I'll leave most of that for the demo that Ashley is going to talk about. So we released the fast anneal protocol across all of our production annealing systems in April of last year, and this is also available on the Advantage2 system, the Advantage2 production solver. Fast anneal is a protocol that allows you to anneal on timescales that are much faster than the timescale for the processor to thermalize or the qubits to actually exchange energy with their environment. So fast anneal gives all of our users the capability to build applications that leverage quantum supremacy, really drive increase and develop increasingly sophisticated quantum simulations. And really the fast anneal protocol has allowed our internal performance research team to fundamentally link increases in coherence and quantum coherence to increases in performance. And so having this capability available across all of our solvers and available to all of our customers is really fundamental. And actually we'll show some nice demonstration of what you can do with the fast anneal protocol. But going back to sort of the role of coherence and linking coherence to performance. So these are data that came from a Nature publication. So this is a research paper that we published in Nature in 2023. Again, using the fast anneal protocol and comparing sort of the performance of the Advantage processor against classical heuristics on driving to low energy solutions to, again, hard spin glass optimization problems. In particular, the results of this paper were, again, we posed problems, spin glass problems to on a qubit lattice structure to the Advantage annealing system, and then we measured sort of how well, or basically the quality of the solutions that came out of Advantage as a function of anneal time. So what we're showing with the data on the right, again, is a similar plot as the one that I showed a minute ago. Along the y-axis is a measure of residual energy per spin. Again, you can think of this as a distance to optimal solution. Again, the lower you are, the closer you are to an optimum lowest energy configuration. But we're plotting this again as a function of anneal time, which is a proxy for computation time, how much time you're spending doing the computation. Shown in the blue data shown with the blue data points are the data coming from the Advantage system. So you can see as we increase the anneal time, we're able to drive down to lower energy solutions. And then what we're showing with the orange data points are the results from simulated annealing, which is a very standard classical heuristic for attacking spin glass problems. And shown in cyan are data from simulated quantum annealing. So this is a quantum-inspired algorithm that is also able to attack these hard optimization problems. I want to make a couple of points about these data. The first is that for the shortest anneal times, we're seeing a scaling advantage. So empirically, the data are driving down to low energy solutions faster and quadratically faster than the classical methods. We're also showing in the coherent annealing regime, so the fastest annealing regime, we're seeing that the sharpest drive down in slope. We're seeing a very good agreement between the empirical data and what you could expect from coherent quantum theory. There's also some expectations that come from classical theory, and so you can see that both the orange and the cyan data follow the classical expectations as well. So fundamentally, we're seeing a scaling advantage. We're opening up a gap with coherent quantum annealing over sort of this, very standard classical methods for solving these problems. The final point I want to make is you can see that this sharp burn down in energy, so the sharp reduction in residual energy per spin, basically slows down when you get to longer anneal times. Really, this is a transition where the longer anneal times, you're annealing for timescales that are long enough, you're starting to allow the system to exchange energy with the environment. So thermalization is starting to play a role and is blunting sort of the burn down in residual energy. So this really shows the boundary between coherent quantum annealing and where you actually start exchanging energy with the environment. And this really, for me, shows the clear power of coherent quantum annealing and delivering the scaling advantage in approximate optimization. And it also shows sort of fundamentally why annealing quantum computing is more robust to interactions with the environment. You can see that the burn down slows down, but the calculation is still delivering lower energy solutions. It's just delivering them at a scale or a basically scaling curve that is slower than the coherent regime. We published about 2 months ago in a peer-reviewed research article in Science, basically a demonstration of computational supremacy or quantum supremacy in quantum simulation. Again, we used a similar set of tools, coherent quantum annealing and fast annealing. We embedded magnetic lattices and different lattice structures in the fabric of an Advantage2 prototype, a smaller scale Advantage2 prototype that has been available in LEAP, basically at the 1200 qubit scale for the better part of a year. And we worked with an international collaboration of researchers, including several researchers at Oak Ridge National Labs, which, that collaboration gave us access to a large amount of compute at the Frontier supercomputer, one of the largest classical supercomputers, are the classical computers on the planet. Fundamentally, what we did was take these magnetic lattices and subject them to a changing magnetic field, which then drove a phase transition in these lattices. And the fundamental question then, the calculation, the computation we're doing was measuring the dynamics of this phase transition. As we're taking these lattices through a phase transition, we're able to actually calculate properties of these lattices with the Advantage2 prototype in a matter of minutes that we're estimating would take for a lot of the largest lattice structures we studied would take up to 1 million years on Frontier. So fundamentally, with this capability, with annealing quantum computing and access to coherent quantum annealing, this is a computational resource that we're harnessing to do a computation, a real-world computation. We're measuring the magnetic material, the properties of magnetic materials, and we're doing it in a way that is completely beyond the scope of classical methods. Though this is a problem that just can't be attacked classically. So this has us very excited. This is opening up a set of use cases in quantum simulation that really are, I think, going to unlock some fundamental value for our customers. And again, this is fundamentally showing that our system, our annealing quantum computing system, can solve a real-world problem that is completely beyond the reach of classical methods. So I spoke about some of these applications. I want to spend a couple of more minutes talking about sort of materials discovery, and then something that we're also quite excited about that leverages sort of the same computational regime to basically do a quantum proof of work to support a blockchain. So I want to spend a couple more minutes on materials simulation. So these are data from a very recent paper, basically hot off the press that just got posted to the archive about a month ago, really showing that we can embed buckyball structures, for example. So, and what we're showing are our figures. What I'm showing the figure on the lower left are some different size buckyballs. So these are basically in nature, these are able to be produced basically with lattices of carbon atoms, and so we can actually embed these buckyballs or these lattice structures directly in our Advantage2 and our Advantage annealing quantum computing systems, and then put frustrated connections or different connections between sort of the lattice sites in the buckyball and study frustration dynamics. And what we're able to do is basically pull out fundamental behavior of these buckyballs in the coherent regime with Advantage and Advantage2, and then compare them against basically the classical predictions for the behavior of these systems. So this is one example of sort of a quantum simulation that you can do with our Advantage2 annealing quantum computer. Elijah will talk a little bit more later in the webinar, sort of on a deeper dive on sort of the tools and what you can actually do with these systems. But this is a set of use cases that we're extremely excited about. This is one example of a series of quantum simulation results that we're unlocking the ability to do with each generation of our annealing quantum computing system. And then maybe a couple words about another application that has opened up, sort of inspired by the quantum supremacy result and the quantum supremacy research. So we were basically thinking about sort of beyond quantum simulation, what can you do when you have basically a real world, a practical computation that's really sort of beyond the reach of classical methods. So one of the things we explored and we developed was both a theory and experimental demonstration of a blockchain architecture where fundamentally what is driving or supporting that blockchain is a proof of quantum work. So basically a quantum evolution very similar to the quantum evolution that supported the supremacy calculation and the supremacy experiments. You can actually do to turn into a quantum hashing function that allows you to basically build a blockchain where you have a network of miners that is basically using this quantum hash to generate new blocks and then add them to the blockchain. So we posted to the archive again about 2.5 months ago this theoretical proposal, this for blockchain architecture, along with an experimental demonstration. What we're able to do is demonstrate across 4 of our production annealing quantum computing systems, geographically sort of distributed across North America, with an ensemble of miners using these resources to build a blockchain. So, and what you're seeing with the animation showing on the lower right is a series of blocks that are getting added by this network of miners. So there's some forking that happens from time to time where there's basically a disagreement, or there's basically 2 potentially valid blocks that get proposed. And then we have a consensus mechanism for resolving this. So you can see, and this is an experimental block, a set of series of blocks. A blockchain is created by this network of miners running on annealing quantum computing systems. So this has us excited for a couple of reasons. One is it's a direct application of this hard computation, the supremacy regime that I spoke about. It is really from the ground up a quantum safe blockchain. So you need a quantum system. You need the fundamental quantum evolution that you get access to with our annealing quantum systems to actually support this quantum hash, this quantum evolution. And that the final thing is that this is energy efficient. So our research and what we published in this paper shows that this could be effectively, orders of magnitude, use orders of magnitude less electricity to run a blockchain as compared to some of the classical blockchains that people are using that basically rely on a classical proof of work. And I think, some of these modern blockchain technologies are starting to consume sort of a very non-trivial amount of electricity. And so this energy efficient application, this energy efficient blockchain has us very excited. And more broadly, this is I think a real value of annealing quantum computing in general, that energy efficiency, the ability to do hard computations with a fraction of the energy footprint. So beyond Advantage2, I mean, we're very excited about Advantage2. We've been busy developing the technology for several years, but we also have an eye toward the future. So, I mean, we pushed fundamentally on connectivity and on coherence and on energy scale, but we also want to scale up our processors and go from the many thousands of qubit scales where we are today to toward processors that have 100,000 qubits in their fabric. So there's sort of 4 areas that we're pushing on in our technology development roadmap today. The first is continuing to innovate on the fundamental processor architecture, further increasing connectivity, further increasing coherence. But we also want to grow the scale of the processor without growing the I/O footprint, without needing to have thousands of lines that go from, say, the control lines that go from the room temperature down to the cryogenic enclosures that enclose our chip. And so we're hard at work on basically laying out and planning a next generation digital addressing scheme that allows us to get to that 100,000 qubit scale without growing substantially the I/O footprint required to control these processors. We're also of the view that increasing our scale really will be accelerated by enabling multi-chip processor fabrics. So these are processor fabrics where the annealing fabric is now built and stretched across multiple processor die. So this allows us to quickly interconnect these processor die and build a larger scale processor with interconnect technology that supports coherent quantum annealing at scale. And so we have an active technology program right now driving toward multi-chip processor fabrics. And finally, as we scale up the size of our chips and as we scale up the size of our processor fabrics, we're investing in larger scale cryogenic enclosures, all of the filtering and the shielding required to actually support these larger scale processors. So I hope I've given you a good sort of taste or a dive into Advantage2, what we're excited about, where we're actually really seeing performance gains, and the use cases that Advantage2 is really opening up for all of our customers and our users. Want to invite all of you to check out our cloud platform, sign up for Leap. So I've got the URL to sign up for Leap. You can actually see code examples. You can see sort of a lot of the applications and the demos that we built out to showcase and use the technology. And actually, we'll actually be running one of these in a couple of minutes. And I also want to invite all of our customers, if you're interested in really engaging, building some applications, really trying out some of these exciting use cases like quantum simulation, quantum optimization, I encourage all of you to sign up for Quantum Launchpad and submit an application. So this is our program that allows some of our users free trial access to the technology to build applications and to investigate a particular use case. And so this gives you 3 months of access as well as some technical advice from a technical advising team. And then finally, we've got a lot of information. We've got resources on our corporate website. So this QR code here will link to a folder, a website or a landing page that has links to the white paper with some benchmarking results, as well as several of the fundamental performance research papers that we've been publishing on our Advantage and Advantage2 annealing quantum computing system. So with that, I want to thank you for your time and attention, and I want to turn it over to my colleague Ashley, who is going to walk us through a live demo of using our Advantage2 system to do a quantum simulation. Ashley.
Thank you, Trevor. Hello, everyone. So yeah, I'm going to stop sharing my screen. I'm going to move over to the web browser, which is where you can go and log on as per signing up for Leap, as what Trevor just talked about. So give me 2 seconds. All right, so today I am going to demonstrate some demos, and we're going to send some commands to the Advantage2 processor, not the prototype. We're going to go to Advantage2 1.1. So what I'm about to use here is what's available if you have a Leap account. So there's a bunch of different types of demos and interactions you can do in sending commands to the processor, to the quantum computer. Today, we're going to be using Kibble-Zurich. So Kibble-Zurich comes from, it started initially in the mid-20th century, started by just the Kibble mechanism from a cosmologist who named Tom Kibble. And he created this mechanism to think about how does a phase transition kind of perpetuate throughout time and how much time would it need to stay ordered or not. So as a cosmologist, he did it applicable to the Big Bang. How did we get from just before the Big Bang to this thermally diverse universe that we now have? So in about 2 decades later, a condensed matter theorist, Wojciech Zurich, he looked at this mechanism and he realized, oh, this actually applies a lot to condensed matter. So when you're talking about phase transitions, so let's say you have like some water and you want to freeze it into ice. If you freeze it using a freezer, it will take a few hours versus just dumping a block of ice or some ice in liquid nitrogen. The way that the atoms will be ordered is going to be very different. So you can imagine that if you're flash freezing water, it's going to be a lot more of a chaotic structure that's frozen into ice. Whereas if you're giving it time to settle into its ice structure, you'll have a lot more ordered system. Another way to think about this is an analogy that I like to use is imagine you're knitting. So let's say I'm trying to knit a sweater. I've never knitted before in my life, so it's not going to be good. So let's say I'm trying my best, but let's also say I procrastinated. My friend's birthday's tomorrow and I really got to get the sweater done. So I'm rushing. So if I'm rushing to knit as a bad knitter, I'm going to get a lot of defects. I'm going to get pull up my sweater, there's going to be some missing stitches, and you'll be able to tell that there's some, what we can say is a kink in the cohesion of the sweater. So if I took more time to knit that sweater, then you can imagine that those defects would lessen in amount. The kink density, what we would call it, would lessen. Now let's imagine I'm actually good at knitting, or let's say my friend Megan is knitting the sweater because she's excellent at knitting. She could probably go as fast as I could, but there's going to be less and less kinks. So this is kind of the idea of going from, as we keep improving our processors, going from Advantage to Advantage2. So with that being said, here we have a 1D chain of spins. So right now we're just in a superposition state, and we're going to, let's just pick a coupling string. So this is literally just spins of qubits on the chain. So a lower negative coupling strength is going to mean, let's say we want our qubits strongly coupled to where they're all going to be facing the same direction. Whereas a more positive, they're going to be antiferromagnetic, where they're going to try and be opposite directions. So let's go ahead and run a command. Let's go to -2. Let's do the strongest uncoupling possible for ferromagnetic. And so we're going to, let's start with 5 nanoseconds. This is in the fast anneal regime that Trevor was talking about earlier. So down here, we also have this graph. And I want to point out this straight white line with this like plus or minus 5, 10%. So this is basically the theoretical limit of Kibble-Zurich. So this is depending on how fast you are annealing, how fast you are allowing a phase transition to happen. This is what you can expect the kink density to be for that time. Purely theoretical, which means you would not expect to see in this theory curve, you wouldn't expect to see any influence of noise. So we're about to anneal for 5 nanoseconds at a -2 coupling strength to the Advantage2 processor. All right, and so now we can see we have some bits that are staying in spin up. So we have this whole chain, kind of this loop right here. This whole chain is in the spin up orientation, but then there's a kink here, and then it goes to spin down, and it kind of keeps going forward, further and further. All right, cool. So that was the fastest anneal. So let's try, I don't know, 30 nanoseconds. Let's see what happens. Let's see what happens when we anneal for longer and we allow the system to reach a more coherent state, cohesive state. Okay, excellent. So now we can actually, that was actually a very beautiful visual a distinction. So now we see it seemed to favor spin down this time. And you can see that just in a difference of 25 nanoseconds, our the cohesiveness, our kink density has dropped dramatically. And this is all available for everyone with a Leap account to log on and play with, along with other demos. Let's do 60 nanoseconds. Let's see what happens then. Okay, excellent. So we see some that are more spin up. And we can also see we're starting to get into a regime where we're annealing for long enough that in the processor, we're starting to feel some thermal just effects of the environment. And this is what DWave is constantly working on, is always trying to improve the qualities and the layouts and the architecture of processors to make sure that we can increase our anneal times and still stay in this like theoretical regime where we're not experiencing any noise from the environment. Any quench duration you want to try, Trevor?
Why don't you try AFM coupling?
Yeah, let's do that. So let's do 0.81. Let's do 1. Let's go crazy. All right, so this is the strongest antiferromagnetic coupling. Let's go back to 5 nanoseconds. And I'm just gonna reselect. Okay, we're all good. Sending it again. All right, so now we can see, it's always nice to start with ferromagnetic because it's easier to see the kinks. But we can see a kink right here. We got 2 spin up right next to each other, but mostly it's looking pretty good. That's why we have a graph to tell us what the kink density is. Yeah, and then we can, let's go down to 50. So yeah, this is all available with a Leap account, along with a bunch of other demos that you're able to access and do. But with that, I can stop sharing my screen and hand it over to Elijah as I share back to the PowerPoint.
Great. Thanks, Ashley.
Thank you. All right, next slide, please. Excellent. Okay, so I'm going to be talking about magnetic hysteresis experiments performed on quantum annealers. I should say at the start that this is work that we are very excited about, which is why I'm talking about it here. But also I should mention that this is unpublished work. We have a manuscript that we are working on, and we hope to be posting as a preprint here reasonably soon. So just keep that in mind. This is all new stuff that we are quite excited about. Yeah, so my name is Elijah Polofsky. I am at Los Alamos National Laboratory, as was mentioned previously. This work was done in collaboration with some other folks at Los Alamos National Lab, Frank Barrows, Pratik Seth, and Cristiano Nasoli. Next slide, please. Okay, so what I'm going to be talking about today is a novel protocol that we have implemented on several DWave processors. This protocol allows us to carry out magnetic hysteresis simulations. And what we're showing on this slide here is sort of a conceptual schematic of how the protocol works on the left-hand side. And then on the right-hand side is sort of a cartoon schematic rendering of a hysteresis loop being sort of drawn out from this protocol. So the way this protocol works is there's essentially three different components. Okay, so the first is our transverse field. This is denoted as gamma, that's the red line. And then our coupling that defines our Ising model, kind of whatever Ising model we can program on DWave, that's defined by our J, that's the cyan line on the left-hand schematic. And lastly, we make use of the H-gain schedule on DWave hardware. This is denoted as H sub Z, or the longitudinal field. That's this black line that's sort of doing a zigzag in the left-hand schematic. Now, what this protocol does is, while we are holding our simulation sort of at a constant proportion of transverse field relative to J, so this is sort of this horizontal pause that you see in the left-hand schematic. While we are in this pause, we ramp up our longitudinal field, and then we very dramatically move it back down, kind of as high positive and as large negative as we can go on the H-gain field. And during this protocol, what we do is we repeat this simulation many times, but we sort of sample at intermediate slices along this longitudinal field sweep. And then if we measure the magnetic characteristics of the samples that we get, what we see is a path dependence. This is what magnetic hysteresis is. It is a path dependence on, the observables that you measure of a magnetic system depend on where you have been previously. In this case, what longitudinal field you have applied previously. Why is this interesting? Well, magnetic hysteresis is sort of arguably like the most fundamental phenomena of magnetism. It's very, very important for understanding magnetic materials. And it turns out magnetic materials of all sorts are very, very useful for all sorts of things, but namely like things like in our electronics and memristors and things like this. So being able to simulate characteristics of magnetic hysteresis is a fundamental kind of capability. And as far as we are aware, no one has simulated magnetic hysteresis, certainly to this degree, say on quantum computers or on quantum annealers to date. To be clear, the main thing here that is different is kind of going through this full field reversal of the longitudinal field. That's kind of the primary thing. I should also note that in the schematic on the left-hand side, we're in data that I'll be showing in a moment, we're only plotting data measured after the vertical dashed purple line. The reason for this is because we want to start in like a fully polarized state. Okay, next slide, please. Okay, so this is real data from a DWave processor. This is one of the Advantage systems, Advantage System 6.4. So here what we've done is we've defined a plus minus J model, okay, on the entire hardware graph of the Pegasus QPU. Okay, so this means that we have basically random frustration. We have competing ferromagnetic and anti-ferromagnetic interactions. So that's the Ising model that we're simulating. Then what I'm plotting is the actual hysteresis curves that we've seen from DWave, from the DWave processor. So the y-axis is our magnetization. The minimum and maximum magnetization respectively are 1 and -1. And then our x-axis is our total applied longitudinal field. Now, the different colors denote different pause locations. So this is different ratios between our transverse field and our J. So what we see is whenever our transverse field is pretty weak, we are able to get nearly full saturation. Whereas when we have very high transverse field, we do not get very close to full saturation at all. That last one is the sort of red-orange line shown here. Okay, next slide, please. So that previous Ising model was fairly densely connected and pretty complicated. This data that I'm showing here is magnetic hysteresis simulation data of a bit of a simpler model. This is also a plus minus J model, but it's now a 2D grid of spins. So it's 26 by 26 spins, and we have embedded this with a spin to qubit mapping. So it's a graph isomorphism on the Zephyr graph. And again, same style of plot representation where our x-axis is our applied longitudinal field, y-axis is magnetization, right? And what we see here is, again, a very clear instance of measured magnetic memory from this simulation, right? So a clear case of path dependence. And being able to examine what is happening during a magnetic hysteresis simulation is a very, very interesting protocol that we are quite excited about. These models that I've just shown data for are sort of relatively easy to define test cases, but they're non-trivial because of the inherent frustration that's built in. And in particular, the reason that we're really excited about this is because when we execute these simulations on the DWave quantum annealers, right, what we're measuring is at the resolution of individual spins. So we're measuring the states of our qubits, and we can do this in the middle of our hysteresis simulations, as well as say at like full saturation, for example. Also, I should mention, of course, this simulation was done on the Advantage2 prototype. And we are working on simulations that also use the larger Advantage system that was newly released. Next slide, please. So this ability to read out properties of these simulations, of these magnetic simulations during hysteresis allows us to do things like extract sort of microscopic observables. Why is this interesting? Well, the thing is that magnetic hysteresis as a whole typically is measured sort of as in bulk materials, right? In bulk physical materials. It is actually reasonably hard, as you might expect, because there's all the magnetic domains and so forth are so small. It's hard to understand all of the characteristics of hysteresis that happen at a very small microscopic scale. So what these plots that I'm showing here are magnetic spin structure factor averaged over 100 configurations sampled during one of these hysteresis protocols, in particular on the Advantage2 prototype. This again is on this 2D square plus minus J model. The key thing I want to say here is not particular observations about the spin structure factor, but rather that we are able to extract the magnetic spin structure factor of the simulation. That's because we are measuring out the states of these qubits, during the simulation. Okay, next slide, please. Yeah, so the paper's coming soon. We hope it'll be on archive within about a week. So be on the lookout for that if you're interested in learning more about this protocol. And yeah, thank you very much.
Great. Thank you so much to all our speakers. We have answered a number of questions during the talks. So if anyone has any additional questions, you can put them in the Q&A box. We'll attempt to answer them in the next 15 minutes. But we do have a number of questions that we wanted to ask our panelists out loud. So Elijah, why don't you come back on camera? There's a few for you as well. The first question that came in, Trevor, what hard problems or algorithms has the 6th generation computer solved? And this was kind of before you talked about some examples, but.
Yeah, I mean, one of the fundamental examples, and I think the most powerful one is so we used our Advantage2 system to perform the supremacy computation. So the material simulation, the materials property computation that we showed is just not it's just not feasible to do in any way via classical methods. And again, this is driven by, the increase in coherence, the increase in connectivity, and the scale of the Advantage2 technology as allowing us to do these computations that are well beyond the reach of classical methods.
Okay, we had a number of questions, as you might expect, relative to quantum and AI. So I will ask this one now. As AI training becomes increasingly resource intensive, how is DWave positioning its quantum technology to support AI machine learning advancements, particularly in terms of collaboration with AI firms and measurable improvements in efficiency, such as reduced training time and lower energy use?
Question. I mean, we're investing heavily on the R&D team here at DWave and really sort of investigating where we can add value with our annealing quantum computing systems to really, like you said, Susan, and the bulk of the question, to really try to kind of bend the cost curve for like how quickly the electricity footprint or the cost footprint for training the frontier models grows. I mean, fundamentally, our QPUs are very good at generating high quality, low energy sort of samples from distributions that can be programmed. A natural fit for our QPU and an overall modern machine learning model is acting as a source of a prior source of high quality samples in a generative model. So some researchers at Triumph High Energy Physics Lab, just outside of UBC in Vancouver, have been using our QPU and training the QPU to provide samples in a generative model that is intended to really reduce the computational cost to doing data analysis of next generation high energy physics experiments. So they're facing a computational crunch in their data analysis pipeline, and so they're really interested in building generative enhanced with these QPU priors to really kind of solve this computational crunch or this computational challenge. We completed a proof of concept work via our professional services team with the pharmaceutical division of Japan Tobacco. They have a use case where they have a classical LLM, large language model, that they've trained on a molecular data set, and they so that it will generate sort of novel molecular candidates that have similar properties to the data set. And so they're really looking at ways of improving the performance of this classical only LLM. And so they worked with our professional services team, again, training the QPU to act as a prior, basically to provide structured novel samples that get trained alongside the LLM. And then in the inference phase, using the QPU to kind of generate novel the QPU and the quantum hybrid model to generate novel molecules and molecular candidates. And what we showed with the researchers at Japan Tobacco is that the quantum enhanced and the quantum hybrid model was able to generate higher quality samples than the classical only model. And so again, we're early days in terms of sort of the impact and the role of quantum computing and our annealing quantum computing technology in the AI space. But there's clear sort of early signs that there's a path forward for really improving and potentially bending kind of the cost curve of training these large scale models.
Okay, thank you. A question for Elijah. What is the role of the transversal field in the hysteresis protocol? Why do you need that?
Yep, it's an excellent question. Yeah, so our study goes into lots of details on this. I will answer. I'll try to answer somewhat succinctly. So, the primary thing it does is if the transverse field facilitates state transitions, it turns out you absolutely need a transverse field in order to carry out this hysteresis simulation. It is the thing that allows you to see dynamics as you're applying this longitudinal field. Now, at the same time, thermal fluctuations do also matter. And this is in the sense of how strong or weak your J coupling is. But yeah, your transverse field is absolutely necessary. So it is the thing that actually allows you to transition states, which means it is the thing that actually among many other components in the DWave QPU, of course, it is sort of the primary thing that is driving you to actually see the hysteresis effect. So, yep.
Okay, thank you. A question for Trevor. Do you have any customers already in production with solutions powered by DWave systems?
Yeah, I mean, a key area of focus and the primary focus of our overall kind of go-to-market effort is really around quantum optimization. And we have 3 customers in production via our technology solving their business optimization problems by running sort of production workflows in Leap. So of examples I can talk about. I can talk about all 3, but I'll drill down into Ford Otosan, who is a customer that just moved into production a couple of months ago. So they came to us. They're basically, their use case is production scheduling of a production line that produces vehicles. And they came to us and worked with a professional services team to work on a formulation that allowed them to better optimize how they switch this production line between a very diverse set of vehicle types. So, and wanting to minimize the number of times they had to switch the production line between vehicle types, but still match overall demand, and then get tuned to, you know, a fluctuating supply chain that's increasingly dynamic and fluctuating as time goes on. And then, you know, inevitable machines sort of availability and just machine types and maintenance schedules. And so what they were doing via the classical methods and the classical only optimization solution, it took them over 30 minutes to solve the problem, and they couldn't represent the full kind of business set of constraints and complexity of the problem. And so they worked with a professional services team. They formulated 4 quantum hybrid optimization solvers, and they got that solution time down to under 5 minutes. But as importantly, they were actually able to layer in all of the constraints that actually made this optimization very valuable for the business. So this is one example of a customer that is solving a business optimization problem with our technology.
Great, thank you. Also, for anyone who is interested, if you go to the DWave website under Learn Featured Applications, you'll see links to either write-ups that have been done, papers. In the case of Japan Tobacco, you can see the presentation that their chief science officer made at our annual Qubits conference just a few months ago. Another question for Trevor. In slide 4, you showcase the gain in annealing time. What about the service time, which is also important in industry?
So let's go back to slide 4 for a second.
You're not there yet.
On the right slide. So what we were able to do with, I think maybe we're frozen. With Advantage2 was more than double coherence time. So within the available anneal times, we're able to get much faster time to solution with Advantage2 over previous generations of our annealing technology. And really this link between coherence, quantum coherence and performance is fundamental. And we've really been able with both internally with the performance research team, and then, you know, we're seeing an increasing number of our users and our customers like really explore that link. Has really pinpointed sort of the importance of increasing coherence as we scale up the technology into the future. And this Ashley talked a little bit about this. She's working on a team that's really looking fundamentally at the sources of noise and sources of decoherence in our overall manufacturing process and our fabrication stack, and really identifying those sources and removing them to increase coherence times going into the future and continue to drive increases in performance.
Yeah, and I think in terms of service time, if you're talking about uptime of the system, then we've achieved over 99% uptime through our Leap cloud service. So clearly, we're very focused on enterprise and real-world use cases.
Yeah, and we're able to support production workflows. Like Susan said, we have very high uptime. We have multiple production QPUs and production systems available via our Leap cloud service. And you could see, you know, just actually running the demos, the Kibble Zurich demo. I mean, this is a real-time platform. You submit problems to the platform and you get answers in real time. So this very much, we've built this technology to be high availability, high uptime in real time.
Question for Elijah. Regarding the magnetic hysteresis study, could this work be expected to have the potential to lower the amount of rare earth elements that may be required for various systems requiring their inclusion?
Interesting. That is a very specific material science question. I am not an expert on rare earth elements and materials science, so the answer is I don't know. But if you have an idea of a model, say an Ising model, that could map to something that can model like a behavior or a material that has rare properties of rare earth elements, then I'd be very interested to see what sort of hysteresis simulations you can do with this protocol.
Okay, thank you. Question, Trevor. How long does it typically take for a customer to go from the stage of modeling their problem in quantum terms to reaching the end stage of getting actual results?
Yeah, that's a great question. I'll give a high level answers. It very much depends on the customer's experience, the actual use case, the business optimization problem, or the problem that the customer is trying to solve. We have an open source tool set, Ocean. So a set of tools that's written in Python that make it very easy to get up and running. We've had some customers basically formulate hard problems on their own in the matter of weeks. So some of our customers go through our training program to kind of get up to speed. And a lot of customers, Ford Autosound as an example, work with our professional services team on a proof of concept, and those typically last some handful of months. So we've had examples of customers get up and running in a matter of weeks to months. And again, it really highly depends on sort of the customer's familiarity with the technology and sort of how well they've really understood the fundamental problem that they're trying to solve. But again, this is we've engineered this technology and the software stack to lower the barrier to make it very easy, or as easy as we possibly can, to formulate for our platform. And we've made it so that you don't need to know detailed physics, you don't need to know detailed sort of quantum computing to actually get value from our platform very quickly.
Okay, we have time for just one more question. So the last one, what would be the difference between an annealing qubit and a gate qubit in terms of properties, usefulness, and coherence?
Fundamentally, the qubit technology, the qubit parametrics that support our annealing architectures are using a superconducting qubit design, a superconducting qubit, or squid flux qubit. So these devices are also we're adapting for gate model architecture. What really matters is sort of how you build the architecture and interaction control of these devices. Annealing architectures look different than gate model architectures. Annealing architectures are quite a bit more resilient to errors. So your requirements on QPU control and QPU coherence are quite a bit easier to achieve with annealing architectures over gate model architectures. But fundamentally, the qubits look very similar between gate and annealing architectures.
Great. Well, thank you so much to all of our presenters, our panelists, and most of all to everyone who attended. We will have our next webinar will be a real world use case on supply chain in mid-July. Anyone who has registered for this will be sending out information about that, along with a link to the recording, as well as if you're interested in the slides, you can just reply and let us know. So thank you all so much, and I hope everyone has a great day.